All right, let's dive right in. We are going on a journey into a world so small it's almost impossible to imagine, to understand the fundamental blueprint of, well, literally everything.
I mean, really think about that for a second. What if you had a manual that explained why a rock is solid, why water is wet, or how the screen you're looking at right now even works?
Well, that manual is real. It's called chemistry. In Chapter 1, the most critical part is all about the atom. This is the basic unit, the foundational Lego brick that builds our entire universe.
So, to get a handle on this blueprint, we've got to start with the parts list, right? We need to peek inside the atom itself.
Tucked away in the atom's tiny, super dense core, the nucleus, you've got positively charged protons and neutral neutrons. Then, zipping around the outside, you have these tiny, negatively charged electrons. Now, they all have a job to do, but it's those electrons that are the real movers and shakers of chemistry.
Okay, and here's the absolute key takeaway. The number of protons is what gives an atom its identity. It's non-negotiable. If it has 6 protons, it's carbon, period. If it has 8, it's oxygen, every single time. It's like a unique, unchangeable ID card.
But here's the twist. While the protons tell you what an atom is, it's the electrons that determine its personality. They decide how it's going to behave, who it's going to interact with. They are the ones doing all the interesting work.
And the thing is, these electrons aren't just bouncing around chaotically. Oh no, they're following a very clear set of rules. And it all comes down to one simple, powerful drive.
And this right here, this is this single idea that drives pretty much all of chemistry. Atoms want to be stable. And for most atoms, being stable means having a full outer shell of electrons. That's their goal. This quest for a full shell is the engine behind every chemical reaction ever.
So how do they do it? How do they get that full, stable shell? Well, to make that happen, atoms basically have two main strategies, two primary construction techniques. It all comes down to what they do with their electrons. They can either give an electron away or steal one. That's called ionic bonding. Or they can agree to share electrons, and that's covalent bonding. Think of it like a transaction versus a partnership.
Let's make this super simple. For ionic bonding, picture this. One atom is a little thief. It completely steals an electron, the bone, from another atom. Now the thief is negative and the victim is positive. And what do opposites do? They attract. That force holds them together.
So that's the fun analogy, but here's the more scientific breakdown. That powerful attraction between the newly positive and negative ions is the ionic bond. It's what holds common table salt, sodium chloride, together so tightly.
Okay, what about the other way? For covalent bonding, let's go back to our puppies. Instead of one stealing the bone, now imagine two puppies are both holding on to the same bone, or maybe two bones at the same time. They're sharing. That way, they both feel like they have what they need.
And the official term for this is, of course, a covalent bond. This sharing creates a whole new, distinct unit we call a molecule. Water, H2O, is the perfect example of this. Oxygen shares its electrons with 2 hydrogen atoms.
Okay, so give, share, ionic, covalent. Why should you care? Well, because this tiny difference at the atomic level literally builds the world you see around you. The type of bond an atom makes directly dictates the properties of the stuff it builds.
And you can see these massive real-world consequences right here. Ionic bonds, like in salt, are incredibly strong, so they form hard crystalline solids with super high melting points. Covalent compounds, like sugar, are a bit more varied. But the most critical difference? Look at that last row. Electricity. This is huge, and we'll come back to it.
Now, for our covalent molecules, there's one more layer to the story. The covalent bonds themselves are like superglue, holding the atoms inside a molecule together. But then you have these much weaker attractions called intermolecular forces that act like sticky tape, holding separate molecules to each other.
And not all of this molecular sticky tape is created equal. No. You've got your weakest ones, London dispersion forces. Then you've got your medium-strength ones, dipole-dipole forces. But the undisputed heavyweight champion, the strongest of them all, is the hydrogen bond.
Which of course brings us to probably the most important molecule of all. We all know water is essential for life, but what actually makes it so incredibly special?
The answer is right there at the top of our chart, hydrogen bonds. These things are powerhouses. They're strong enough to give water all its amazing properties, like its incredibly high boiling point for such a small molecule, and its famous ability to be a universal solvent, which is absolutely essential for life.
Okay, let's bring this all home, right into your own body, because these aren't just abstract rules in a textbook.
These are the rules that are literally running you right this second.
Hey, remember a few minutes ago we said ionic compounds can conduct electricity when they're dissolved? Well, there's a special name for them, electrolytes. When you dissolve something like salt in water, it breaks apart into positive and negative ions that can just float around.
And this is why you hear so much about electrolytes in sports drinks. Because that solution of mobile ions, that's your body's electrical wiring. Every single nerve impulse, every thought you have, every muscle contraction, it's all powered by the flow of these charged particles. They're the spark of life.
So when you really step back and look at it, from the nuclear furnaces inside stars to the firing of a neuron inside your brain, everything follows the same fundamental rules, the same blueprint. It's all about achieving stability by giving, taking, or sharing electrons. So if we truly understand this instruction manual, what else can we build? What comes next?